All right, in today's lecture, we're going to cover the section 6.1 material on power series. So this starts our chapter 6 material, which is the last bit of material for our course. And this chapter 6 stuff is all about power series. So in this section, let's start by introducing what exactly is a power series. So here, a power series is any series of the following form. The sum from n equals 0 to infinity, where our general term is given by c sub n times x minus a to the nth power, where x in this setting is a variable, a is a constant, and these terms c sub n are constants, which are referred to as the coefficients of this power series. So this sort of power series, something in this form, is said to be centered at A. We're going to see why we would use that terminology in just a moment, but in this case, where we have something of the form x minus a to the nth, we would say this is centered at A. Now, these power series are series that depend on a variable x. So the values of x are going to determine whether this series converges or diverges. So for a power series, what we're going to be interested in doing throughout a big part of this chapter is determining the set of all x values such that this series will converge. So the name that we would give this set is the following: the set of values of x where a power series converges is called its interval of convergence, and it's denoted as capital I for interval. And we could then define something called the radius of convergence as half the length of the interval of convergence. And the radius of convergence is denoted by capital R. So we have a few cases for the radius or interval of convergence for a power series. There's three possibilities for what the interval or radius of convergence of a power series would look like. So let's consider that we have a power series of general form, which is centered at x equals a. Then there are three cases which we're going to discuss here. The first case is the worst case scenario. And this says that this series would be convergent only at a single value of x, namely x equals a. So we see here, well, if x is equal to a, then this x minus a to the nth term is equal to 0. So our infinite series would just be the sum of a bunch of 0 terms, so the sum would be 0. We're guaranteed convergence always at the value of x wherever we center this series. So the worst case scenario that we would have for a power series, if we think about visualizing this, we have the x-axis representing the set of values for x where this series converges. And this worst case says that we have convergence only at a single value x equals a, and we would have divergence everywhere else. So every other value of x would cause this series to diverge, but we do have convergence at a. So in this case, the interval of convergence, that is the set of all x values where our series converges, would just be an interval consisting of a single point, x equals a. That's sometimes called a singleton. And the length of the interval of convergence would be 0, because this interval consists of a single point. It doesn't have any length. Now, the next case that we'll consider is that our series converges for all values of x. This is the best case scenario, where no matter what value we have for x on our number line, we're guaranteed convergence. So our power series could be thought of as being centered at A, and then for every value of x, we have convergence. So in this case, our interval of convergence would be the entire real line, that is from negative infinity to positive infinity. And the radius of convergence, which would be half the length of that interval, is infinity. So if we have the entire real line, the length of half of the real line would still be infinite. And then one of the more common cases would be the following. There exists some number r greater than 0 such that our series converges if the distance between x and a is less than r, and it would diverge if the distance from x to a is greater than r. So let's visualize this. If we have our real number line of x values, we can consider this as being centered at x equals a. And we know that this series will converge if the distance from x to a is less than r. So that means I can move r units to the right of a. I would have a plus r, or r units to the left of a. So I would have a minus r. And everywhere within that open interval, I am guaranteed that my series converges. However, we have our series diverging if the distance from x to a is greater than r. So if I move farther than r units to the right of a, I start to see divergence. Or if I move r units further than r units to the left of a, I would see divergence. So we have some subset of the real line for which our power series converges. And in this case, we have convergence everywhere within this open interval from a minus r to a plus r, and I have divergence everywhere on the open interval from a plus r out to infinity, or from negative infinity up to a minus r. So then the question becomes, well, what about these endpoints? A minus r and a plus r. Both of these inequalities that we were looking at above were strict inequalities. So the question is, well, do we have convergence or divergence at the endpoint? So in this sort of case, we have to test the endpoints individually to determine what our interval of convergence is, to decide if either of those endpoints would be included. So let's look at some examples of how we would determine the radius or interval of convergence for a given power series. So we'll look at a few of these. In our first example, we are asked for the radius and interval of convergence for this power series. And just to review a little bit of the terminology that we were introducing in this section, I could think about writing this in the form 2 to the n over n squared plus 1. And then my x to the n I can think of as x minus 0 to the nth power. So here we would see, if we rewrite it in this form, this power series is centered at x equal 0. So let's see if we can determine the interval or radius of convergence for this series. Now for most power series, for all power series based off the definition, they all have to include some term of the form x minus a to the nth power. And we had discussed that for any series that involves some constant being raised to the nth power, a good choice for the test for convergence would be the ratio test. So for any almost any power series, the first thing that we want to try is the ratio test. Now, to apply the ratio test, we look at the limit as n approaches infinity of the absolute value of the n plus 1 term of our series. So here we would have 2 to the n plus 1 times x to the n plus 1 divided by n plus 1 squared plus 1. And then we divide by the nth term of this series. But recall that the nth term is usually a fraction, so rather than dividing by that fraction, equivalently we could multiply by its reciprocal. That is n squared plus 1 over 2 to the n times x to the n. So here we have the limit as n approaches infinity of the absolute value of, well, let's see what terms can be simplified here. So inside of our absolute value, well, we have 2 to the n plus 1 divided by 2 to the nth. So I can cancel n powers of 2, and I'm left with 2 to the first for my numerator. I also have an x to the n plus 1 over x to the nth. So if I cancel n factors of x, I have x to the first in my numerator. So for our numerator, we have a 2 times x times n squared plus 1. And then we are dividing by n plus 1 quantity squared plus 1. So here we notice that this one term, 2x, does not depend on n. And here we're taking a limit as n approaches infinity. So if this constant, the absolute value of 2x, does not depend on n, that means I could pull it out in front of this limit. So I would have the absolute value of 2x times the limit as n approaches infinity of n squared plus 1 divided by n squared plus 2n plus 1 gives me plus 2 for my denominator when I expand that n plus 1 squared. Now what happened to the absolute value? Well, since n is always non-negative here, this quotient will be positive. So the last step to take our limit, we would look at what happens as n approaches infinity. And in this example, we have the infinite limit of a rational function with the same highest power of n on top and bottom. So our limiting value would be the ratio of the lead coefficients, which is 1. And then we had our constant absolute value of 2x out in front of that. So our limiting value here is the absolute value of 2x. And we know that by the ratio test, in order for this series to converge, this limiting value needs to be less than 1. So let's say this. By the ratio test, this power series converges if the absolute value of 2x, that is what we found for our limit using the ratio test, is less than 1. So let's solve this inequality for x now. So here we could think about this. If the absolute value of a quantity, 2x, is less than 1, that means that the quantity inside of the absolute value has to be less than 1, but greater than negative 1, so that its absolute value is less than 1. So solving for x, I would divide through by 2, and I find that the series converges for all values of x from negative 1/2 to positive 1/2. So we're working with that third case for the interval of convergence for our power series. Here, if we visualize this, if we think about our x interval, we were centered at 0 for this power series. And I know that I have convergence on the open interval from negative 1/2 to positive 1/2. And I would have divergence if the absolute value of 2x, that is the limiting value that I found here for my ratio test, would be greater than 1. So anywhere outside of that interval, I have divergence. I have convergence within the interval. And then the question becomes, well, what about the endpoints? What about when x is equal to plus or minus 1/2? So if x is plus or minus 1/2, then the limit that we found for the ratio test would be equal to 1. And remember, if that limiting value for the ratio test is equal to 1, then the test is inconclusive. We don't know about convergence or divergence. So we have to test those endpoints individually. So let's look at the first one. The right endpoint of this interval was x equals positive 1/2. So let's see what we have. If x is equal to positive 1/2, then let's see what we have for our series. So looking at this general form for the series that we started with, if we plug in x equals 1/2, we would be left with the sum from 0 to infinity of 2 to the n times 1/2 to the n, which would reduce to 1 over n squared plus 1. So let me write that out in a little more detail so you can see exactly what I'm doing here. So we have a series from 0 to infinity of 2 to the n times x to the n. Now if x is 1/2, I have 1/2 to the n over my n squared plus 1. So if we simplify, our numerator, 2 to the n times 1/2 to the n is 1 to the nth power, which is always 1, divided by n squared plus 1. So if we want to determine the convergence or divergence of this series, well, there's a few ways that we could do it. One way would be to make use of the direct comparison test. This series would be dominated by the series 1 over n squared. So here, because we were adding, since we had 1 over n squared plus 1, if I were to omit that plus 1 term from the denominator, I get a series which is even larger. That is the sum of 1 over n squared, which is a convergent p-series. So we could say the following. Since the sum of 1 over n squared converges by the p-series test, with a value of p equal to 2, which is greater than 1, the series converges by the direct comparison test, so we tested that right endpoint, x equals positive 1/2, and we saw that the series converges at that right endpoint. So we have to consider now our left endpoint of the interval. So if x is equal to negative 1/2, then our series, which was the sum from 0 to infinity of 2 to the n times negative 1/2 to the n, since x is negative 1/2, over n squared plus 1, becomes the sum from 0 to infinity of negative 1 to the nth for our numerator, divided by n squared plus 1 for our denominator. So this is an alternating series, And to determine convergence or divergence of an alternating series, we want to make use of the alternating series test. So our first step in that test is to determine what is a sub n for this alternating series. In this example, we would have 1 over n squared plus 1. So recall, we're looking at what we get if we ignore this negative 1 to the nth power, which just alternates the sign between plus minus 1. So here we would be left with just positive 1 over n squared plus 1. And there are two things that we need to check for the alternating series test. The first is that the limit as n approaches infinity of a sub n, which was 1 over n squared plus 1, is 0, which we see it is indeed 0. And 2, the second thing we have to check is that the sequence a sub n is decreasing. So here, if we look at a sub n plus 1, that is 1 over n plus 1 quantity squared plus 1, which is certainly less than if we just had 1 over n squared plus 1. Since my denominator would be less for the n plus 1 term, I would have a larger term if I just considered n squared plus 1. But this is a sub n, so we have shown that the sequence a sub n is decreasing. So we can say that our series from 0 to infinity of negative 1 to the n over n squared plus 1 converges by the alternating series test. So we have shown that our series converges at both endpoints, when x is equal to 1/2 or when x is equal to negative 1/2, we still had convergence. So for this example, we would say that the interval of convergence would be given by capital I equals the closed interval from negative 1/2 to positive 1/2. We include both endpoints, and we denote that by using square brackets for those endpoints. And then the radius of convergence, which would be denoted as capital R, is half the length of this interval. So the length of the interval from negative 1/2 to positive 1/2 would be 1, and then we're taking half the length of that interval. So here we found our interval and radius of convergence for this power series. All right. So again, what we're finding here are the set of all x values that I could plug into the given power series, and I am guaranteed convergence. So let's look at another one. In this next one, we have the sum from 0 to infinity of negative 2 to the nth times 2x minus 1 to the nth power over n plus 1. So again, if we want the interval or radius of convergence, we're going to try the ratio test first. So the ratio test says we look at the limit as n approaches infinity of the absolute value of the n plus 1 term, which is negative 2 to the n plus 1, times 2x minus 1 to the n plus 1, over n plus 1 plus 1, or n plus 2, times, or divided by the nth term, but since the nth term is a fraction, equivalently we can multiply by its reciprocal, which was n plus 1 divided by negative 2 to the nth times 2x minus 1 to the nth. So let's see what we can simplify here. So in the numerator, we have a factor of negative 2 to the n plus 1. We're dividing by negative 2 to the nth. So if I cancel in factors, I'm left with negative 2 to the first in the numerator. We also have 2x minus 1 to the n plus 1 divided by 2x minus 1 to the nth. So if I cancel in factors of that term, I'm left with 2x minus 1 to the first. So far, in our numerator, we have negative 2 times 2x minus 1. And then we've got that extra factor of n plus 1 that appears in our numerator. And then we are dividing by, I had n plus 1, or n plus 2 for my denominator. So, as we did in the first example, we notice that this negative 2 times 2x minus 1 is a constant with respect to n. It doesn't depend on n. So I can pull it out in front of my limit. And so I have the absolute value of negative 2 times 2x minus 1 times the limit as n approaches infinity of n plus 1 over n plus 2. So this last part where we have the infinite limit of a rational function, again we have the same highest power n to the first on top and bottom. So my limiting value is the ratio of those coefficients. So I'm left with the absolute value of negative 2 times 2x minus 1, or taking the absolute value of each part, well, the absolute value of negative 2 is positive 2 times the absolute value of 2x minus 1. So by the ratio test, I know that the series converges. So let's say by the ratio test, this series converges, provided that this limiting value, which was 2 times the absolute value of 2x minus 1, is less than 1. So let's solve this inequality for x. So here, I could think about it like this. In order for 2 times the absolute value of 2x minus 1 to be less than 1, that means that the quantity 2 times 2x minus 1 would have to be less than 1 and greater than negative 1. So if I divide through by 2, I have negative 1/2 is less than 2x minus 1 is less than positive 1/2. So adding 1 throughout, I have 1/2 is less than 2x, which is less than 3/2. And lastly, dividing through by 2, I would have 1/4 is less than x is less than 3/4. So again, we're working with that third case for our interval of convergence. So if we visualize this, we have our number line x, and here the center of that interval from 1/4 to 3/4 would be 1/2. And I know that my series converges everywhere between 1/4 and 3/4. So I can move 1/4 of a unit to the right or 1/4 of a unit to the left, and I know that this series converges within that interval. Now, outside of that interval, we have divergence. If this limiting value, 2 times the absolute value of 2x minus 1, is greater than 1, that is, if I lie outside of this interval, I'm guaranteed to have divergence. And then the question becomes, well, what about the endpoints? If this limiting value, 2 times the absolute value of 2x minus 1, is equal to 1, then we would have x is equal to 1/4 or 3/4, and the ratio test is inconclusive there. We have to try some other test to consider those endpoints separately. So as with the last example, let's look at our right endpoint. If x is equal to 3/4, Then let's see what we have for our series. So we have the sum from 0 to infinity of negative 2 to the nth times 2x minus 1. Now if x is equal to 3/4, then 2x minus 1 would be 3 halves minus 1, or 1 half to the nth power over n plus 1. So simplifying, we have the sum from n equals 0 to infinity. Our numerator becomes negative 1 to the nth, and the denominator is then n plus 1. So again, this is an alternating series. So to determine convergence, we need to apply the alternating series test. So for this series, a sub n is 1 over n plus 1. And there's two things that we need to check for the alternating series test. The first is that the limit as n approaches infinity of 1 over n plus 1 is equal to 0. Clearly it is, since our denominator keeps getting larger as n approaches infinity. And the second condition, number 2, is that the sequence a sub n is decreasing. So if we look at a sub n plus 1, we have 1 over n plus 2, which is certainly less than 1 over n plus 1, which was our a sub n term. So the sequence a sub n is decreasing. So we can say here that the series from 0 to infinity of negative 1 to the n over n plus 1 converges by the alternating series test. Now we need to test our other endpoint, that is the left endpoint of this interval, which was x equals to 1/4. So if x is equal to 1/4, then our series is from 0 to infinity of negative 2 to the n times. So if x is 1/4, then our 2x minus 1 to the nth is 1 half minus 1, so negative 1 half to the nth, all over n plus 1. So simplifying, we have the sum from 0 to infinity of positive 1 over n plus 1. So looking at this series, we could determine its convergence or divergence by using a limit comparison test. Our general term is a rational function, 1 over n plus 1. So it looks like it's pretty similar to 1 over n, the harmonic series. So let's compare with the harmonic series, 1 over n. So using the limit comparison test, we would take the limit as n approaches infinity of the ratio of the terms of our series. So the series that I'm considering is 1 over n plus 1. We divide that by the general term of the series we're comparing with, which is 1 over n. And this gives us the limit as n approaches infinity of, dividing fractions, we would have n over n plus 1. So that's the infinite limit of a rational function with the same highest power of n on top and bottom. So we get a limiting value of 1, which does lie in the interval from 0 to infinity. So the limit comparison test says that either both these series converge or they both diverge. So since the harmonic series, the sum of 1 over n diverges, by the p-series test. That means that the series that we were considering of 1 over n plus 1 also diverges by the limit comparison test. So we had divergence at the left endpoint of 1/4. So to finish out this problem, our interval of convergence, I, would be everything from 1/4, but not including 1/4, up to 3/4. And when x was equal to 3/4, we had convergence. So we would include that right endpoint. And then the radius of convergence, r, is half the length of that interval. So the length of the interval from 1/4 to 3/4 is 1/2. So taking half of that length, we would have 1/4 for our radius. So here, interval and radius of convergence are given by the following. All right. So we see in these first two examples that in that third case of the interval of convergence, where it converges on a subset of the real line, not just a single point or the entire real line, that we have to test the endpoints, and this can get a little bit tedious. Now, the other two cases we'll consider in our next couple of examples, and that's a little bit easier to handle. So for the following power series, we are asked to determine the interval and radius of convergence. And we see immediately that our general term involves a factorial, so that suggests we should try the ratio test, or for these power series problems, that's always the first thing we want to try anyways. So we're going to look at the limit as n approaches infinity of the absolute value of the ratio of our terms. So the n plus 1 term would be n plus 1 factorial times x minus 4 to the n plus 1 power. And then we are dividing by 9 to the n plus 1 plus 1, so 9 to the n plus 2. And then we divide by the nth term, but since the nth term is a fraction, that we can then multiply by its reciprocal. So 9 to the n plus 1 divided by n factorial times x minus 4 to the nth. So this gives us the limit as n approaches infinity of, well, let's see which terms can be simplified. So here we could start with the constants 9 to the n plus 1 divided by 9 to the n plus 2. So if I cancel n plus 1 powers of 9 on top and bottom, I'm left with 1 power of 9 in my denominator. Now we can also look at this x minus 4 to the n plus 1 over x minus 4 to the nth, and canceling n factors of x minus 4 on top and bottom, we're left with x minus 4 to the first for our numerator. And lastly, we could consider these factorial terms. We have n plus 1 factorial divided by n factorial, which gives us an n plus 1 in the numerator. So altogether, we are left with x minus 4 to the first times n plus 1 in our numerator. And in the denominator, we have a 9 to the first. So what I'm left with, if I pull out my constant terms in front of the limit with respect to n, we have the absolute value of x minus 4 over the absolute value of 9, which is just 9, and then times the limit as n approaches infinity of a n plus 1. So what we find here is the following: is n becomes infinitely large, n plus 1 diverges to infinity. So we have an infinite limit for which would be greater than 1 for all values of x which are not equal to 4. So what is this x not equal to 4 business about? Well, in the event that x is equal to 4, this term in our power series, x minus 4 to the nth, would be equal to 0. So we would be summing 0 infinitely many times, and we would have convergence in that case. So we find, using the ratio test, that the limit of this quotient is infinite, which is greater than 1, for every value of x except 4. So by the ratio test, the series converges only for x equal to 4. So in this example, our interval of convergence would be the singleton, that is the interval consisting of a single point, x equals 4, and the radius, which would be the length of that interval, or half the length of that interval, is 0, since the interval has no length. So here we have a power series centered at 4, and we had convergence only at that value. For every other value of x which was not 4, that factorial term in the numerator made our series grow without bound, so we had divergence. All right. So in this case, we don't have to consider any separate endpoints, so this is one of the easier cases to consider. Now, in our next example, we'll consider the best case scenario. So here, we're asked for the interval and radius of convergence for this power series. So we know we want to use the ratio test. We might also suspect that from the appearance of a factorial term in our series. So we would look at the limit as n approaches infinity of the absolute value of the ratio of our n plus 1 term, which is negative 1 to the nth, times 3x to the n plus 1, so negative 1 to the n plus 1, 3x to the n plus 1, divided by, when I plug in n plus 1, I have 2n plus 2 plus 1, so altogether 2n plus 3 factorial, divided by the nth term, or equivalently multiplying by the reciprocal of the nth term, which is 2n plus 1 factorial, over negative 1 to the nth times 3x to the nth. So let's see which terms can be simplified and what we're left with. So in our numerator, we had a negative 1 to the n plus 1 over negative 1 to the nth. So canceling n powers of that, we are left with a factor of negative 1 in our numerator. Then we had a 3x to the n plus 1 over 3x to the nth. So canceling n powers of 3x, we are left with 3x to the first in the numerator. And then lastly, looking at these factorial terms, we have a 2n plus 1 factorial divided by 2n plus 3 factorial. So the 2n plus 1 product down to 1 will cancel with all of the terms from the 2n plus 3 factorial, except for the terms which didn't appear, which would be 2n plus 3 and 2n plus 2. All right. So now, let's see what we're left with. We have, for our numerator, the absolute value of negative 1 times 3x. So that's the same as the absolute value of positive 1 times 3x, times the limit as n approaches infinity of 1 over 2n plus 3 times 2n plus 2. So taking this limit as n approaches infinity, well, we see that our denominator grows without bound. So 1 divided by these infinitely large values is a ratio which is shrinking to 0. So this limiting value is 0, which is less than 1. And that was true regardless of what this constant out in front was. So regardless of what we choose for x, we get a 0 limit, which is less than 1 for all values of x, which are real numbers. So here we can say that our interval of convergence would be the entire real line. That is the interval from negative infinity to positive infinity. And the radius of convergence, r, would be half the length of that interval, which is infinite. So here we would have the best case situation where no matter what we choose for x, we're guaranteed that this series converges. So we've illustrated now all of those cases that we had considered for the interval and radius of convergence. So let's look at one more of these. I get a little extra practice here. So in this one, we have the sum from 2 to infinity of 3 to the nth x minus 1 to the nth over log n. So again, to find the interval or radius of convergence, we're going to apply the ratio test. So we take the limit as n approaches infinity of our n plus 1 term, so 3 to the n plus 1 times x minus 1 to the n plus 1 over the natural log of n plus 1, and we divide by the nth term, or equivalently multiply by its reciprocal. That is the natural log of n divided by 3 to the n times x minus 1 to the nth. So we have the limit as n approaches infinity of the absolute value of, well, let's see what we're left with. So here we have a 3 to the n plus 1 divided by 3 to the nth. So canceling n factors of 3, we're left with 3 to the first in our numerator. We also have a x minus 1 to the n plus 1 over x minus 1 to the nth. So canceling n factors, we are left with x minus 1 to the first in our numerator. And then we have the quotient natural log of n divided by the natural log of n plus 1. So pulling our constant out in front of the limit with respect to n, well, we have a constant of 3 times the absolute value of x minus 1. And then we're left with the limit as n approaches infinity of the natural log of n divided by the natural log of n plus 1. So this limit is a limit of indeterminate form, infinity over infinity. So we would need to make use of L'Hopital's rule. So we have our constant out in front, 3 times the absolute value of x minus 1 times the limit as n approaches infinity, and we look at the quotient of our derivatives. So the derivative of our numerator, natural log of n, is 1 over n, and then we're dividing by the derivative of our denominator, which would be 1 over n plus 1. So let's see what that gives us. We have 3 times the absolute value of x minus 1 times the limit as n approaches infinity of, well, dividing these fractions, we're left with n plus 1 over n. So we have an infinite limit of a rational function with the same highest power n to the first on top and bottom. So we have a limit of our constant, 3 times the absolute value of x minus 1 times the ratio of those coefficients, which is 1. Now, we know that by the ratio test, the series will converge if this limiting value, 3 times the absolute value of x minus 1, is less than 1, or equivalently, if the absolute value of x minus 1 is less than 1/3. So if the absolute value of x minus 1 must be less than 1/3, that means that the quantity x minus 1 inside the absolute value is less than positive 1/3, but greater than negative 1/3. Or adding 1 throughout this inequality, we would have 2/3 is less than x, which is less than 4/3. All right. So here again, we're working in that third case for the interval of convergence. On our number line x, we have a power series centered at 1, and we can guarantee convergence by the ratio test on the interval from 2/3 to 4/3. So I can move 1/3 units to the left or right of 1, and I'm guaranteed convergence. And outside of that interval, 3 times the absolute value of x minus 1 would be greater than 1, so I have divergence by the ratio test. And then the question becomes, well, what about these endpoints? At x equals 2/3 or 4/3, we would have a limiting value when we apply the ratio test of 1, and so our test would be inconclusive. We've got to try something else. So let's consider these endpoints separately. At the right endpoint, where x is equal to 4/3, let's see what our series becomes. We have the sum from 2 to infinity of 3 to the n times, if x is 4/3, then x minus 1 is 1/3 to the nth over the natural log of n. So this becomes the sum from 2 to infinity of 1 over the natural log of n. So here we can determine the convergence or divergence by the direct comparison test. 1 over the natural log of n is always greater than the sum of 1 over n to the first power. We can make use of a direct comparison here. So since this series, which is smaller, is the harmonic series, which we know diverges, then the larger series, 1 over the natural log of n, must diverge by the direct comparison test. So let's say the following. Since the sum of 1 over n to the first diverges by the p-series test, with the value of p being equal to 1, that means that our series from 2 to infinity of 1 over the natural log of n also diverges by the direct comparison test. So x equals 4/3 will result in a series that diverges, so it is not included in our interval. And then let's look at the left endpoint of that interval. If x is equal to 2/3, then our series is the sum from 2 to infinity of 3 to the nth, then x minus 1 would be a negative 1/3 to the nth over the natural log of n. So we have an alternating series, negative 1 to the nth over the natural log of n. And to determine the convergence or divergence of an alternating series, we have to apply the alternating series test. So here we're going to work with a sub n is 1 over the natural log of n. And there's two things that we have to check for the alternating series test. The first is whether the limit as n approaches infinity of our general term, 1 over log of n, is 0, which it is since the natural log of n is increasing in the denominator. And the second condition is that a sub n is a decreasing sequence. So here a sub n plus 1 is 1 over the natural log of n plus 1, which is less than 1 over the natural log of n, since logarithm, the natural log is an increasing function, but this was a sub n, so it is also a decreasing sequence. So we can say the series from n equals 2 to infinity of negative 1 to the n over the natural log of n will converge by the alternating series test. So in this example, we find that our interval of convergence would be from x equals 2/3, including that left endpoint 2/3, up to 4/3, but not including 4/3, since we saw it diverged when x was 4/3. And our radius of convergence would be half the length of that interval. So here the length of the interval from 2/3 to 4/3 is 2/3. So half of that interval would be 1/3. All right. Now in the last part of this section, we'll consider some conceptual problems in determining the interval and radius of convergence. So in this last one, let's suppose that it is known that the series from 0 to infinity of c sub n times x to the nth power will converge when x is equal to negative 4, and it diverges when x is equal to 6. So then we're asked about the, what can we say about convergence or divergence of these certain related series. So in this example, we are looking at a power series whose coefficients c sub n are unknown. Here we don't know what exactly c sub n is, but then we have x to the n, which we can think of as x minus 0 to the nth. So here this power series is centered at 0. So let's think about a visualization for the interval of convergence. If we think about a number line of x values, we're centering at 0, and we are told for this series that it converges when x is negative 4. So at x equals negative 4, I know that that value is going to be contained within my interval of convergence. And since we're centered at 0, well, if I know I can move 4 units to the left of 0 and have convergence, I know that I can move at least 4 units to the right of 0 and still have convergence. But I can't say anything for sure about that right endpoint at 4, just because the left endpoint at x equals -4 would be included in the interval of convergence. We have seen that that does not always mean our right endpoint of +4 would be included. So I'm guaranteed convergence within that interval. And I am also told for this problem that the series diverges for the value x equals 6. So at x equals 6, I know that I have divergence. So if I move 6 units or farther away from 0, we have divergence. So it follows that if I were to move 6 units or further to the left, I would also have divergence. Now I can't say anything about when x equals -6. So I know that I would have divergence for sure at x equals 6, but I could have convergence all the way up to 6, but not including it. So I can't say anything for sure about this left endpoint -6. So let's look at the series that we're given here. In part A, we have the sum from n equals 0 to infinity of c sub n. So here, if we don't have any term appearing after c sub n, that means that our x value would be 1. We're looking at 1 to the first power here. So maybe we could think about writing that in there. The sum of c sub n's we could think of as c sub n times 1 to the first power. So x is equal to 1 in that case. So if x is equal to 1, well, we know that that is included within our interval of convergence. So we can say here that this series would be guaranteed to converge. Now for part B, we have the sum of c sub n times 8 to the n. So if x is equal to 8, we see that that lies in our interval of guaranteed divergence. So we could say that that series diverges. Now in part C, we have the sum from 0 to infinity of c sub n times 4 to the n. So here x is equal to +4, that is this right endpoint. And remember here that we could not say for sure whether that right endpoint was included or not. Just because the left endpoint of -4 was included does not mean we can say anything about the right endpoint with certainty. So here I can make no conclusion. And in part D, we have the sum from n equals 0 to infinity of c sub n times -5 to the nth. So here x is -5. So -5 would lie in this interval. And we can't say for certain in that interval whether we have convergence or divergence. It doesn't lie within our intervals where we have a definite result. So here we would have to say, again, no conclusion. All right. So even if we don't know what the coefficients of our power series are, if we know that it converges for some particular value of x or diverges for another value, we can guarantee convergence or divergence for some other related power series. So let's look at one last example that's similar to that. In our last one, we have the sum from 0 to infinity of c sub n times x minus 1 to the nth. So this power series is centered at x equals 1, and we're told it converges when x equals 4. So then the question is, on what interval are we certain that this power series converges? So let's think about visualizing this again. We have a number line of possible x values for convergence, And here our power series is being centered at 1. Now we were guaranteed that we had convergence at x equals 4. So I can move 3 units to the right of 1 to get to 4. And so, since we are centered at 1, I know I can move at least 3 units to the left of 1, so that would be to -2. But I can't say for certain whether this left endpoint would be included. So it may be included, it may not be included, but I am guaranteed convergence on the open interval from -2 to +4, with 4 being included. So here we can say that we are guaranteed convergence on the interval -2 to +4, with 4 being included. All right. So in this section, we've introduced a power series along with an interval or radius of convergence for a power series. And we've seen that depending on what type of series we're working with, our interval could be consisting of a single point, the entire real line, or some interval of finite length within the real line. And we can determine from guaranteed convergence or divergence of a power series, the convergence or divergence of that power series for different values of x. Now in the remainder of our Chapter 6 material, we'll start looking at operations that we can perform with these power series and how to represent functions as power series in order to manipulate